Alright, welcome back to our fifth part of the lecture. Now, to be honest, this last part here, I rearranged the slides several times and I'm still not convinced I have it in the best possible way. We'll muddle our way through though, okay? We've talked about things like other components of the hydrological cycle, like precipitation, evaporation, low-level humidity, mid-tropospheric humidity, and so on. What about something as obvious as cloud cover? I mean, cloud cover is clearly going to be important when it comes to climate change because of the role of clouds in the Earth's radiation budget, as we're going to be seeing, and so on. And you would think that this would be easy. I mean, it doesn't take any special equipment to go outside and look at the clouds and decide how cloudy it is, and you could look out there like this guy is and tell me how much cloud cover there is, but it turns out that's actually really hard. It turns out even skilled weather observers will come up with considerably different estimates as to, like, is that 40% cloud cover, or 50% cloud cover, or 60% cloud cover. And often the observer isn't particularly all that well trained. I mean, some observer on this ship, merchant ship at sea, is going to have to decide how much of the sky is covered with clouds at this time. Is he going to come up with the same answer as the observer on the next shift, and so on? It's just too hard. There's just too much uncertainty in manual observations of cloud cover from the ground. And the truth of the matter is we're better at that. From satellites, but even that's not great. The truth of the matter is, when satellites look down, it's actually quite difficult to decide whether an individual pixel is cloudy or clear or not. And even then, the satellite record is just not that long yet. We haven't been using satellites this way. One satellite will be launched, and then another satellite will be launched with different equipment on board, so there's inhomogeneities in the data set. The truth of the matter is we can't really show long-term trends globally using the satellite data archive yet. It seems like this should have been possible, but it turns out that observations of things like clouds and precipitation are really, really hard. Part of the story is that they're so variable in space. For example, let's look at precipitation totals. Here's the precipitation totals from some storm system, I have to admit I can't even remember, that came ashore in South Carolina. When you actually take a look at these rainfall totals, look how close they vary. Even over very small distances, you can have a factor of 2 in differences in precipitation. If you are looking at the precipitation at some station and then you wonder what it rained 5 miles away, it could be quite different. I mean, we just aren't. There's so much variability with respect to space and time in precipitation and in cloud cover that it's very hard to have a sampling strategy that actually holds up under any kind of rigorous scientific statistical analysis. I mean, the variance in precipitation is so high from one event to another that even like a 30-year climatology of precipitation is still kind of a mess. Let me give you an example here. Here's a 30-year climatology of precipitation that I got from the UNL website for Nebraska. And you can see how broadly it is drier out in western Nebraska and it's more moist in southeast Nebraska and so on. But when you actually look at those little contours and all those little areas where there's a little bit more rain and a little bit less rain, do you think that's real? Do you think those little places with those little like for some reason it just rains a little bit more right there and then a little bit less right there? No, all those little wiggles and stuff in there, that's just how the contours look because of all the variability in the precipitation data. You know, there's just so much variance with respect to space. I'm sure in the real, like if we had perfect rainfall information, this would be a very smooth transition from drier conditions in western Nebraska to wetter conditions in eastern Nebraska. But there's so much variance in the precipitation that it's hard to see that. It's hard to find that kind of statistical analysis. In fact, here's a GPCC, what is that? The Global Precipitation Climatology Center or something. This is the precipitation normals globally. And even these global in situ observations, well, I mean, if you actually look closely at them, they're kind of a mess. I mean, there's all kinds of little, one pixel's quite a bit different than the adjacent pixel. That's not real. Well, actually, it might be real. That's the problem. We don't know which is real versus which is just sampling problems. That particular station just got hit a few times just by chance when other areas around it didn't. This is a mess. These kind of precipitation climatologies are not good when they're being taken from in situ rain gauge stations. Now, in some ways, we can do better with satellites because satellites can have very high resolution, and we can come up with estimates like this one from the Global Precipitation Climatology Project, where satellite-based remote sensing measures of precipitation have been used to produce maps of precip, but these are, if anything, too smooth and they actually have bias problems. Remote sensing of precip is a very, very hard topic that's actually a subject of much ongoing research. Here's another database. This is from TRIM, the Tropical Rainfall Measurement Mission, which was a satellite with a down-looking radar. And you can see that it has different kinds of products that estimate the amount of precipitation, and they all have problems. I mean, they have strange little unrealistic gradients and so on. It's just really hard. There's too much variability. If your satellite just happens to pass over when the rain is falling, and 5 minutes later the rain stopped, the satellite doesn't know that. If the satellite passed over the edge of the precipitation and thinks that that the rainfall continued off to the east from there, there's no way to fix that. Okay, satellite estimates of rainfall are not so great, and frankly, it's hard to do it with clouds too. Just taking a satellite image and actually unambiguously deciding which pixels in this image are clear and which pictures are cloudy is surprisingly difficult. It's the kind of thing scientists argue about at scientific conferences and write competing papers about and so on. And it's really hard. And that's before you start saying, gosh, any individual pixel on this image might be a mix of clear and cloudy. There might be places below in that pixel where we are seeing all the way to the surface and other places that are cloudy. For that matter, we don't know anything yet about how high the cloud is. There are satellites that can, instruments that can measure or estimate how high the cloud is, or what kind of cloud it is, or whatever, but it's getting really tricky and really contentious. Different scientists are going to have different ideas about how to do it. This stuff about these aspects of the hydrologic cycle are just really, really complicated. And you'd like to be able to compare it to ground truth data, like actual manual observations of the clouds, but as I mentioned, that's horrible too. This is part of the problem for estimates of cloud cover from satellite, is we don't even have good ground truth to compare it to know what the right answer is. This is going to be hard. We probably can't get a handle on this in the observations, is what I'm trying to say. Which makes us all the more grateful for what we were able to do when it comes to humidity. When it comes to humidity, it was actually relatively easy to observe using simple equipment. It has a fair amount of variability over short distances at any given time, but averaged over a period of days, weeks, months, years, those gradients get relatively smooth. We have relatively straightforward patterns to the precipitation. We see to the humidity. We see, oh, it's drier over deserts, it's drier over polar regions, it's more moist in tropical regions. Because the patterns of humidity are smoother and easier to measure, and there's ground truth, we can actually go out there with in-situ measurements and measure ground truth and then calibrate satellites against it and so on. This is a relatively easy thing to work with. Okay, and well, that's both good and bad news. The good news is the humidity is going to be part of the radiation budget of the Earth. We're going to need to understand that if we're going to understand global warming. The bad news is we're going to need to understand clouds too. And clouds are a big part of global warming and how they reflect radiation and how they emit radiation. So the hydrologic cycle's got some problems. It's just trouble. What we've seen today is that a warmer world should be a more humid world, and by and large the observations did agree with that. And we saw that a warmer world should overall be a rainier world, and the observations sort of showed that, especially north of about north of about 60 degrees north. We saw that actually regionally several places were definitely more moist, especially like Central North America and so on. Okay. And we saw from theoretical reasons that a warmer world should be having more runoff down the world's rivers. Now that we didn't have very big confidence on. The observations don't seem to show that yet. Or whatever. And then there were all these issues of like cloud changes and snowfall changes where we weren't even sure whether we think it should be more or less. The core problem with the observations for the rainfall and the clouds was this, that the observations were too poor. We don't have good enough observations to compute a trend that actually has meaningful interpretation. This is a big problem. Now, in the next lecture, we're going to start off by talking about what this means for weather patterns we're going to be seeing, and then we're going to start launching into what does this mean for the ocean, what does this mean for the cryosphere, and so on. But in the meantime, as we finish up this very long lecture, let's answer three more questions. Question 12. Suppose that the observations from a particular manned weather station show an increasing trend in cloud cover over a period of decades. However, during that time, the way the observers were trained to measure cloud cover changed. This would be an example of blank in the data: inhomogeneity, intermittency, or evidence of global warming. What does it mean? We had this problem when we were changing how we were training the observers. Make a choice from those three options and get a little feedback before you move on to question 13.